So good evening and welcome to the CAPS Forum on Ethics and Public Policy. My name is Greg Jarrett. I represent the Walter H. Capps Center for the Study of Ethics, Religion, and Public Life. It's part of our mission to bring in distinguished speakers to help elevate the level of discussion about matters of ethical import. And so that's one thing that we're doing today. Tonight's speaker is from the University of California, San Diego, where he teaches in the Department of Pathology and is director of the Research Ethics Program at the School of Medicine and Office of Graduate Studies and Research. He is also co-chair of the Embryonic STEM Research Oversight Committee. Dr. Kalichman is trained in engineering and also in neuropharmacology. He has taught research ethics for over 25 years. He is the founding director of the UC San Diego Research Ethics Program, and we've had some conversations about ethics in setting this up. And one of the things we're trying to do is to reach out to STEM students, science students, because ethics doesn't just belong in philosophy departments or in humanities or in religious studies. We're all doing ethical work, or whether we know it or not, work with very serious ethical implications. So I do thank my students for coming, but and members of the community, but also those students in STEM programs who are interested in hearing this talk. I'm very, very pleased to see that you're here. He is the founding director, back to our speaker. Dr. Kalichman is the founding director of the UC San Diego Research Ethics Program, the San Diego Research Ethics Consortium, and the Ethics Service for the UC San Diego Clinical and Translational Research Institute. Further, he is co-founder of the Center for Ethics in Science and Technology. Dr. Kalichman has taught the trainer research ethics workshops throughout the United States, as well as Central and South America, Africa, the Middle East, Europe, Asia, and you haven't been to the South Pole yet. Oh, okay. The moon. The moon. Finally, he created the Resources for Research Ethics Education, one of the first online resources for teaching of research ethics. Tonight's talk is called Research Ethics: Uncertainty, Reproducibility, and Truth in Science. Please welcome Dr. Michael Kalichman.
Okay, so good evening. Is this microphone working? Can you hear me at the back of the room? Okay, great. A couple of things to add after that. So the first one is, I am used to people showing up because they have to show up, not because they chose to show up. I teach scientific ethics courses at UC San Diego, and it used to be that when I would ask how many of you are here simply because you want to be, some people actually did raise their hands. But now almost everybody that is present for those courses is there because they're required by their graduate program or because of an NIH training grant. And so this puts a burden on me regularly, which I have tonight as well, which is I don't want you to feel like you've wasted your time. I'm going to do my best to give you some horrific horror stories for you to regale your friends with so that you won't think it was a total loss. The other thing is, Greg mentioned that all of you are doing ethical research. I want to stipulate that I hope most of you are doing ethical research, and that we know that some people aren't. And sometimes not being ethical can be as simple as not paying attention to what you're doing. It's not that you're a bad person, but you aren't paying attention, and can that really be ethical if you're using various resources? Okay, so I'm going to launch into what I have here for this evening. I'm going to begin with a large focus on personal, because that's how I got to where I am. That's where I got to what I'm thinking about. And so I'm going to begin with my undergraduate program. You don't have to know exactly when it was, but it was in the last century. I was a student at Revelle College at UC San Diego. And I still remember, and I told Greg this when we were talking about what this program would be like. I still remember going to the orientation the summer before classes were supposed to start, and the provost of Revelle College got up at the front of the room and talked about what we were going to be doing, and drew this circle connecting arts and humanities and sciences and engineering, and was making the case that these things are all connected. No one of them is, in some sense, meaningful without its connections to all of the others. And whether or not you believe that or agree with it, I can tell you that it had a profound impact on me. And so just at an unconscious level, almost at every stage of my subsequent career as an undergraduate student, graduate student, and later as a postdoc and faculty member in San Diego, I kept focusing on this idea of breaking down the barriers between those different, somewhat artificially constructed disciplines, and instead trying to examine specific questions that might arise and figuring out how to address them with all of those factors involved. I left UCSD after finishing my undergraduate program to go to the University of Toronto. I received an undergraduate degree in applied mechanics and engineering sciences with a specialization in bioengineering. I kept somewhat of a similar theme by going to the University of Toronto by getting a master's degree in electrical engineering with the Institute of Biomedical Engineering, and then decided to make a slight shift to neuropharmacology for my PhD at the University of Toronto. Came back to San Diego. I'm going to talk about something at the University of Toronto in a moment on the next slide, but came back to San Diego, and eventually, after being a postdoc and becoming a faculty member, I founded the research ethics program, as Greg mentioned. That was in 1997, so it's been around for a while, and it so far has only known me as the director. Early on in the history of that program, I was invited by a philosopher who was teaching a course on ethics for undergraduate students to come in and talk about the use of animals in research. And after that talk, she and I started talking about the barriers, the walls between the divisions of the campus. On the one side, you had the arts and humanities, to some degree social sciences, and on the other side was the medical school, and somehow people couldn't walk across that divide, which was basically a street called Gilman Drive. It was not that hard a street to cross. And so we came up with the idea of founding a biomedical ethics seminar series where people from these diverse disciplines could come together and wrestle together with the questions that came up in various ethical issues. And that seminar series is still ongoing. The philosopher Mary Devereaux now is the person who has been coordinating that on her own for some years, and it's something that's under the research ethics program, or affiliated with research ethics program that I've been running. That's the biomedical. And then finally, another expression of this is something that came out of that seminar series, which is the realization that some of the biggest ethical questions in science and technology aren't the science and technology per se, but it's how we as scientists and engineers deal with the technology. Specifically, the failure to engage with the general public and the community about what we're doing, why we're doing it, understanding what their perspectives are, and getting their ideas and realizations that sometimes we as scientists might not have. So that program has been going on since 2004, engaging the general public in those kinds of conversations. So what you just heard lays the seeds for the kinds of things that have happened with me and that are parts of the argument for the discussion tonight. So I said I went to the University of Toronto, and I've got a PhD in neuropharmacology. So when I finished my master's degree, I've identified a faculty member in pharmacology who looked like the perfect person to do a dissertation with. He was still relatively young, but a pretty smart guy, and he had just discovered what appeared to be a very specific receptor in the brain of rats for a drug that was used for treating a disease. At this time, for those of you who know that kind of field, it was a really big deal. Looking for receptors in the body for known drugs would help you to understand where those drugs were attacking in the body, better understand the diseases that were involved. And so the idea of doing this was really attractive. And I thought this is going to be a great project, and he had such good data. So I went to the lab with this guy, and this is also from the last century, obviously. And the idea of the experiment has to do with reproducibility, ultimately, because the goal was to look at the specific binding of this drug molecule to tissue from rat brains. And without going into the details of the experiment, what you should understand is that ideally what you'll see is that there will be a displacement of the drug that has been bound to these receptors, and it's very hard to displace the last bit if it's really tightly bound. So you want to see how much is bound there. And so you should see a curve that where you look at the concentration of drug you're washing out with, you should see a curve when you look at the percent binding as you increase the concentration you're washing out with. But when I did the experiment, I got this, which is basically noise. It doesn't look like there's any difference from the lowest concentration to the highest concentration. And my recollection is that I worked day and night for 3 months, but that's probably only how it felt. It might have been 3 weeks. It was enough time that it was very painful. Show of hands, how many of you would at this point decide that I need to find another degree or another program? Anybody? That seem obvious to anybody? So one person, okay, just Greg. So I wasn't thinking that, I was just thinking there's something wrong with me, that I just don't know what I'm doing. But I finally had the insight to ask the professor whose lab I was doing this in, can I see your original raw data so that I can try and sort of see where I'm going wrong? And without hesitating, he said, that's fine. It's in my office. I'm going to a meeting this weekend. Just go in there and have fun, look through it, figure out what's going on. So I went to his data, and I found that his data looked just like this, except before he reported them, he did some work on his data, which was to throw out the points that didn't look right, and he ended up with beautiful binding curves. And at that point, I knew something was wrong. And so I went to another professor in the department that I had worked with indirectly as a master's student and asked him what I should do. And this person knew this professor that had done this well because they were good friends. And he said, I don't know what's going on there, but why don't you come and work with me? So I did, and that's where I got my PhD. I never considered that I would sometime later find myself in a career working on research ethics. The idea of whistleblowing was completely foreign to me, whether I should have done something or what I might have done. So, what should I have done here? I'll tell you right now, if you're ever in this situation, a really compelling case can be made that you should do something about it. Not just for yourself, but for the institution of science, for the protection of other scientists, perhaps to help get the person who's doing this on the right track. What should he have done? Obviously, he should not have been throwing out data points without apparent reason other than that it made his data look better. But it's so hard for me to understand because my recollection is this was a smart guy who should have understood the risks of what he was doing, that he's going to be creating something that might, in fact, not be real. And I, to this day, don't know whether he knew what he was doing, whether he knew it was wrong, whether he had some reason that maybe it was a good thing to do. I don't know. And that's the result of nobody pressing the question with him. And if he didn't know that it was wrong, is it still wrong? And clearly, I hope you can see there is still something wrong with it. Even if he isn't unethical, even if he isn't a bad person, evilly creating data where there wasn't data in the first place, that's still a problem because that means somebody else trying to do the same thing won't be able to reproduce it. And so that's kind of the subject for today. And fundamental principle, I decided to devote one slide to these words, that good bioethics, good ethics on almost any circumstance that has to do with the world in which we live, starts with good data. And we need to therefore ask, when we are looking at the data for any question, acutely, the question that a lot of us are thinking about is coronavirus. So how good are the data about its risks and where people might be affected and how much it takes to become infected with serious illness and what the risks are of dying, it is right now very much a moving target. And those data are helping us to make ethical decisions. And I would argue an ethical decision is one such as, when do you close down your borders? When do you quarantine someone? For how long do you quarantine them? Who gets treatment? Are masks useful? And I hope most of you know that for most of us, masks are almost never going to be useful for this. But what is the real, what is the ethical question here has to be answered by having a clear picture of what the data tell us. In science, then, what is the structure that helps determine whether we're going to be providing appropriate, useful data? There is a premise that I hope you've heard, which is you get what you reward. So if you are rewarding something for X, you shouldn't be expecting Y. You're going to get X because they are going to be working towards what they are rewarded for. This idea can be traced to or paralleled with Charles Darwin's view of natural selection. Any variation, if it be in any degree profitable to an individual of any species, will tend to the preservation of that individual and will generally be inherited by its offspring. In science, any sort of reward system that you create that causes individual scientists as a group, to gravitate towards that thing, those are the ones who are going to succeed because that's what success is defined as. What does the scientific community reward? Well, in terms of quantity, most of us are really well aware that we are rewarded for having more publications, which does not inherently mean better science, better work. It just means more publications. And bizarrely, and I'm going to be talking about this a bit tonight, bizarrely, in order to assess quality, we often resort to asking not what is the quality of your work, not what is the quality of this publication, but what is the quality of the journal you published in. And we judge the quality of the journal you published in by how many times people cite publications in that journal. I'll come back to that, and I hope you can already see that's not going to give us good research. That's going to give us people trying to do everything they can to get into those what are called high impact factor journals. The result of these things, and many others, but the result of things like this is that we increase the risk of research that is not reproducible. Not being reproducible means that it isn't reliable in a way that we can say, this is what we would want to treat as the truth. So the format of tonight is that I'm going to sort of touch on 4 different areas. One is the reproducibility aspect itself. Second is a little bit about statistics. And I will not be getting deeply into any statistical formulae or otherwise, but talking about statistics in more general terms. Third, that journal impact factor piece. And fourth, what kinds of solutions we might have. And my plan is to leave enough time towards the end because I plan to learn more from you tonight than you learn from me, because I want to hear your ideas on some of this. So I don't know how many of you have seen this paper. Actually, has anybody seen this paper before? John Ioannidis? I know you probably have, Andy, but just, okay, only a couple of you. So this was published in 2005. I think I'm trying to remember, 2005, does that sound right? Yeah, so, and the title says what is demonstrated in a theoretical way very strong in the paper, why most published research findings are false. And that is not something we would like to believe, but what Ioannidis showed was that the things that we do, many things that scientists commonly do, any good philosopher could tell them that's not a good idea, are problematic. Using small studies, increasing the chance that if you do enough small studies, some of them are going to come out positive. It's going to look good, but in fact, you might just be looking at random variation in the same way. If I say I'm going to flip this coin and let's see if it comes up heads, sometimes it will come up heads. If the effect sizes are smaller, that's the magnitude of difference compared to how variable the data are. If there are a lot of possible test results you can choose from, and then you decide after doing the tests, you decide which ones you're going to choose, you have a chance of finding something that isn't, in fact, true. When I was a professor initially at UCSD in the anesthesiology department, I was basically only the second PhD in the department. Everybody else was an MD. So despite the fact that I had no real training in statistics, my training was that I was the only person in my pharmacology graduate program who stayed awake during the statistics lectures because of my engineering background. So I had that much level of understanding of statistics. People came to consult me, and when they did, they would more often than not come to me and say, I have these two groups of subjects, and I measured these 50 things in those two groups of subjects. And I went and did a t-test on all of them, and look, numbers 17 and 42 are statistically significant. Can you tell me what I should be doing about reporting this and analyzing the data? And I would try to explain to them, and unfortunately, usually I'm not sure I was successful, that it would be surprising with that many comparisons if they didn't see something that they theoretically could report as being a positive result. We can go into that a bit more later, but at any rate, having a lot of things you can choose from means that you can find something that works. Just as I could say, these coins always come up heads, and then I flip a bunch of coins, and I only look at the coins that say heads and say, see, they came up heads, and just ignore the others. I've come up with a false result, as if I've done something appropriate. Having greater flexibility in your designs, definitions, outcomes, and analytical methods also gives you a chance to find something that is in fact not true. Things that push us towards positive results, like a greater financial or some other interest or prejudice, will tend to favor us doing studies in a way that shows what we want to see, putting emphasis on the studies that show us what we want to see. And as a result of that, again, we report what we found because we think this is real, but in fact, we just chose by selection what we wanted. And finally, lots of people chasing what is called statistical significance. I just realized that for those of you who aren't in experimental science, actually, how many of you are in experimental sciences? Should find out about that. Okay, and how many of you would say you're more in the humanities, social sciences, those areas? I shouldn't lump those together because there's some distinct difference between the two. How many just humanities? Okay, so for the humanities people especially, there's a standard that we use in the published literature for experimental research. And the standard is that there should be less than a 5% chance that we are wrong about something. So I'm going to actually come back to that in a little bit, but this is what they're talking about here when they say chasing statistical significance. Something is statistically significant if we say there is less than a 5% chance I'm wrong. Not a very big chance, and again, we'll come back to that. So these are factors that might lead to reproducibility problems, and recently the scientific community has been, at least on paper, deciding we have a crisis in reproducibility. This is a study that was published in Nature a couple years ago, 4 years ago now, where they've surveyed researchers and found that an overwhelming majority of them believed we do have a crisis in reproducibility. What's interesting is that the level of problems with reproducibility may not have actually changed, but people are now paying more attention to it. There have always been some risks of this. So let me talk to you about what level of problem we have with reproducing what has already been published somewhere else. In other words, somebody else did the experiment, and now I'm going to try and do the same experiment. Can I reproduce their findings and find something similar? And this is from psychology. And what Simmons and co-authors decided is that if you don't bother to disclose how flexible your data collection and analyses happen to be, you can, as a result, present almost anything as significant. The implication being that you could just pick almost any bizarre correlation you might see in the world and say, I'm going to find it. And then if you give yourself enough flexibility, you can find it. Just doing effectively what that professor did with the data in San Diego when I was a potential PhD student in his lab. So flexibility in data collection, analysis, and reporting dramatically increases false positive rates. In other words, people reporting things ostensibly true things at some level, that they're supposed to be true, but in fact, that's a false positive finding. In many cases, researchers are more likely to falsely find evidence that in effect exists than to correctly find evidence that it does. So fairly disturbing about psychology, and consistent with that is a paper that was published in 2015 where a bunch of psychologists got together trying to replicate 100 experiments and correlational studies, and only 37% of those studies could be reproduced and still be statistically significant. So one very loose way to think about that is you got 100 studies that are supposed to be true, everybody's treating them as true, and now we're trying to repeat them, and if they were true, we should be able to repeat them, and only 37% of them were true. Now at this point, I suspect some of those of you who raised your hands for experimental science, especially if you're in the biomedical sciences, may be thinking, well, what do you expect of psychologists and social scientists? But do not speak up about that too soon, because the real attention to the reproducibility crisis came because of two major papers on reproducibility in the biomedical sciences. And remember that it was 37%, only 37% of the psychology studies are reproducible. These studies are based on, in both in case of drug companies, are based on an understanding from venture capitalists. They kind of just know, the people who've got the money, they know that at least half of published studies in top-tier academic journals can't be repeated. So you don't want to base your science, your clinical science that will hopefully be a treatment at some day, with blindly on what's been published, because it may not be reliable. So at Bayer, they looked at 67 projects, 67 pieces of work that they thought were important and promising, mainly in the field of oncology. And then what they found was in almost 2/3 of the projects, inconsistencies between published data and in-house data in most cases resulted in termination of the projects. For the record, that means that this wasn't 37% as psychology, this is about 33% reproducible, so less than psychology. And that was not fully replicable, that was at least partially replicable. A second study around the same time from Begley and Ellis from Amgen Company, again, primarily oncology trials, looked at 53 landmark papers that were deliberately selected to be completely new, such as fresh approaches to targeting cancers or alternative clinical uses for existing therapies. But these are papers that looked promising. They were thinking, this is where we want to put our effort. And what they found that they could confirm findings in only 6 of those 53 papers, which is 11%. So a conclusion I draw from this is that psychologists are better trained in statistics than biomedical scientists. And Andy, who I know is working on this, probably has a lot to say about that part as well. So what is true? I am not a philosopher, but I have a great deal of respect for philosophers. So I'm not going to pretend to be an expert on defining the truth. But when we say what is true in science, we use this as our standard. We say if you reach the level of probability less than 0.05, probability less than 5%, you would be wrong. And I hope everybody, including the people who have routinely published papers this way, realize what a low bar that is that we are giving ourselves to say we are deciding this is the truth. Here's 20 dots. Let's assume that this is 20 times you might cross the street at this intersection. And I'm going to tell you there's only a 5% chance you'll be killed when you cross at this intersection. How many of you feel that's enough reassurance to know that it's safe to cross at that intersection? And most of us, I know there's a certain percentage of you who are thrill seekers, and that'll be just fine. You love jumping out of airplanes and similar things, but for the rest of us, that's not very reassuring. I mean, would I stake my life on that? Now, you don't want to think of yourself staking your life when you publish a paper, but the fact is, researchers rely on what people before them published, and we treat what's been published before as if it is the truth or the correct information about what we're studying. So where did that come from? Because it is kind of bizarre, and this is the guy who first came up with that number, that idea. His name's Ronald Fisher. He also was busy during the last century, earlier than me. And he came up with this idea of P equals 0.05. Probability equals 5%, or 1 in 20, that chance that you'd be wrong. He said it was convenient to take that up as that point as a limit in judging whether a deviation should be considered significant or not. Now, when I say a deviation being significant or not, what he meant was that his work was a lot on agricultural crops, so they had different fields of plots of land, and they wanted to try different variables that might promote crop growth or not, and see which ones were effective and which ones weren't. So he came up with statistical methods to do that, and came up with this cutoff of saying something was of particular interest. It was significant if it reached that level of 5%. The irony is he did not mean that to be definitive, that this is the answer to whether something is true or not. He intended it only as a very informal way to look at what you're doing and judge whether things are worthy of a second look. So in theory, we shouldn't be publishing just because we got P equals 0.047. We should be then saying, this is worth another look, and let's design a more rigorous, thorough experiment to make sure that what we think we're seeing is valid and, in fact, part of the truth. So I told you that 5% is not a very rigorous standard. So what about 0.00001? And reading a few years ago about the history of statistics, I came across this concept of moral certainty. This is Georges Louis Leclerc de Buffon, who talked about moral certainty, which in 1777. It is the same in all the games, the bets, the perils, the risks. By the way, that's where people tended to look at probability, was in betting games and so on. That's where some of the first work was done. Where the probability is smaller than 1 in 10,000, it must be, and it is in fact for us absolutely zero. So if you can get to that level, it's close to zero. So an interesting thought experiment would be, how would it change the scientific literature if we decided publication requires you to reach the level of less than 1 in 10,000 chance of error instead of 1 in 20 chance of error? And I can tell you one thing that would change clearly, which is that we would have a lot less to read. So it would be a lot easier to do our research, but we wouldn't have as much data out there to work from. So this is the term that he and others used, moral certainty, that we are that certain that this is true. All right, so doing okay on time. So I want to move on to journal impact factor as I think an important driving factor for people not paying sufficient attention to things that would help ensure the reproducibility of their work. Because good, reproducible work that others can follow, requires a lot of time and a lot of effort and often a lot of resources. So what has happened is that people are, in almost every graduate program I've talked to, they are thinking a lot about the impact factor of the journal they might publish in. It's become a surrogate for deciding this is the right place to publish, and therefore, if my work is in there, my work must be particularly good. This is related to that concept you've heard of publish or perish, which is driving people to say, I've got to publish. If I don't publish a lot, I'm not a good scientist. I'm not a good academic. And the incentives are asking us to publish a lot, publish it in those journals, and people are doing what's called p-hacking. For those of you who haven't worked in experimental sciences, and maybe even some of you who have, that term refers to the idea of seeking that magical number less than 0.05. And to give you an idea of how that's played out, in a number of studies, people have looked at the published papers in a field, one after another, and then calculated the actual precise p-value based on the data that they had generated. And as you would expect, they're under 0.05 because they have to be in order to be published in most of these cases. But what they found was there is an intense clustering of values just under p equals 0.05. P equals 0.049, 0.048, 0.499. So I hope you can all quickly see that nature did not design itself so that when somebody studied nature, you would just barely get under 0.05 when something is true. So how did it happen that so many papers end up clustering under that value? And the answer was illustrated by Ian Eadie's paper, that these people are doing whatever they can to get the result they need. I taught statistics for about 10 years for neuroscience graduate students at UCSD, and one of the exercises I would go through with them was getting a set of data on the board and saying, let's do a t-test on this data and see whether it is statistically significant. Are the two groups different? And I demonstrated that you can come up with sets of data where with any of various standard tests you might use, if you test that data with one of those tests, it'll be statistically significant. It'll make it. But if you test it with the other tests, it won't be. And you might say, well, which is the right test? Well, the right test is the one you decided to use the first time. It's not the one you decided to use the 4th, 5th, or 20th time looking for a test that will give you the answer you want. So that is an example of the kind of thing that p-hackers do. They keep looking for one test after another till they find something that gives them the answer they want. And they convince themselves, as the anesthesiologists did in San Diego, well, if I had just studied this in the first place, that number would have been the same number, so why can't I do that? And the answer is because you are basing your decision to use that test on prior information. There's something else that you know that has caused you to now choose to do that. So the test no longer means the same thing. So what is this journal impact factor that is helping to push all of this, and how is it calculated? So this is the calculation. And for those of you who are in fields where you perhaps aren't paying as much attention to this, I will reassure you that most of the scientists who are paying an inordinate attention to this number don't know about this either. And I'm going to try and help all of us become at least aware of what we're doing, even if we don't decide to change. So the impact factor of a journal is calculated by looking at the number of citations during the preceding 2 years. So if we started December 2020, we want to look at all of the citations back to January 1, 2019. So that 2-year period, the number of citations to articles in that journal that were published in that journal. But there's also a modifier word there, citable items. So it's not everything that was published in that journal, it's the things that have been decided to be something that you can cite, which allows opportunities for people to game the system in various ways. So before I talk to you about that gaming, where did that impact factor that I just described come from? It came from this guy, Eugene Garfield, and he is responsible for a number of things. His paper about this was in 1955. But actually, before I tell you about that, his comment about this, Eugene Garfield is responsible for things like Science Citation Index, current contents, and I hate to do this to those of you who are old enough to remember, but how many people here besides me used to go through current contents? Anybody? Nobody? Oh boy, I've got a whole group of people that aren't familiar with current contents. So as a graduate student in the life sciences, in the last century again, so what we did each week is we received a printed copy of current contents. It was simply a printing of the tables of contents of every journal published in the life sciences. At that time, it was possible to make a little booklet, pamphlet. It's about that thick and about this big. And a scientist in those days would actually read through all of those tables of contents, not restricting things to a Google search and saying, I just want to find what I want to find. we would see everything that was being published, and we would run across things that would be interesting, different directions we might take in our research. Science has changed since then, but that current contents was one of Eugene Garfield's creations. So a really important person in the metrics for publication. This is Garfield's comment on the use of the impact factor. The source of much anxiety about journal impact factors comes from their misuse in evaluating individuals. In many countries, I have found that in order to shortcut the work of looking up actual, real citation counts for investigators, the journal impact factor is used as a surrogate to estimate the count. I've always warned against this use. There is wide variation from article to article within a single journal, as has been widely documented. Not to put too fine a point on it, but if your journal doesn't have a lot of papers in it, just one paper in that journal could be responsible for all of the citations. It says nothing about all of the other papers in that journal. And this is illustrated very well by this journal, which, for the record, I have never read other than reading about this story about the journal. It's a real journal, and its impact factor was less than 0.7. For those of you who aren't familiar with looking at impact factors, journals like Lancet and Nature and Cell have factors on the order of 30, 50, 70, so much higher. What those numbers mean is in a 2-year period, you have that many citations on average per paper in the journal. And most of us, we are lucky if anybody ever cites our papers. So that's a pretty big number. And this journal was down at the bottom of less than 0.7. And the editor started thinking about this and thought, this is a silly system, and it would be nice if our impact factor was higher. So as a reaction to that trend, he and some other authors decided to put together a review of articles published in their journal during the past 2 years. So this required them to cite every single article that was published in their journal in the past 2 years. And this increased their impact factor to greater than 1.4. It more than doubled their journal impact factor by writing this one almost joke paper where they said this is how many papers were from different countries, this is how many papers, I don't remember what kinds of things they looked at, but they had a variety of ways they could categorize the papers that they'd had. The result was that they were removed from the journal citation reports for impact factors for the next 2 years. So they were penalized for doing this. And yet, it's a reminder that there probably are lots of ways that you could game this system. For example, remember I said that it's the number of citations of papers over a 2-year period. This is calculated only once each year after the year is ended. So we can't get an impact factor for journals for 2020 or 2019. It's too early because we don't know those numbers yet. We have to wait until the end of the year before we can look back further. So if you recognize that, then you would realize that if I've got 5 papers that I think might get a lot of citations and I'm just ready to publish them and it's December, that's going to hurt me because if I publish them in December, there's very little time for anybody to cite those papers before the end of the year. So it would be to my advantage to hold off and not release those papers until January. And then they'd have a whole year to get further citations. Now, some of this may sound really absurd, what I'm talking about, but I'm trying to demonstrate the absurdity of what we emphasize as what's important in science and what we reward. So here is the defense of using impact factors for judging somebody's career. The impact factor, this is from a guy named Huffel. Impact factor is not a perfect tool to measure the quality of articles, but there is nothing better. And it has the advantage of already being in existence and is, therefore, a good technique for scientific evaluation. Experience has shown that in each specialty, the best journals are those in which it is most difficult to have an article accepted. And these are the journals that have a high impact factor. Most of these journals existed long before the impact factor was devised. The use of impact factor as a measure of quality is widespread because it fits well with the opinion we have in each field of the best journals in our specialty. Now, I read that, and at some level it resonated. I thought, okay, that makes some sense. I can see why you would make that argument. But then I thought of a parallel argument in defense of judging the health of individuals by solely looking at their body temperature. Body temperature is not a perfect tool to measure the state of health, but there is nothing better, and it has the advantage of already being in existence and is therefore a good technique for medical evaluation. Experience has shown that for most life-threatening infections, the best predictor of ongoing health is normal body temperature, and these are the cases in which someone is most likely to still be alive. So I hope you can see we don't want to go to the emergency room and have them say, we're just going to take your temperature and decide whatever else needs to be done based on that. We want them to look at the whole picture. And yet, routinely, I have seen scientists so often rest everything on what is the impact factor of the journal I might publish in. I want to publish in high impact factor journals. If I'm not doing work that can go into those journals, then I'm not doing good enough work. And this is an argument that you would think would not be made by really smart people. In my experience, academics are in certain ways really smart people, but we end up spending so much time focusing on something like impact factor. All right, so I'm going to start wrapping up now. So there are lots of causes of failures to reproduce published work. They might be because the person trying to reproduce somebody else's work is doing it wrong. And that's certainly quite plausible. Maybe you're just not as good at doing it as somebody else was. You're sloppy, you're not paying attention. There's lots of reasons. And that's an issue, but it's not the biggest issue we should be worrying about here today. A second issue is that it could be fraud. You know, somebody is making stuff up, and it would not be surprising if we couldn't repeat what somebody had simply made up, unless they are trying to make up things that are known to already be true or appropriate. The third is where it gets more interesting. That's where there are failures of design, documentation, or what we report that will make it hard for somebody to reproduce what we've done. And those failures could be intentional, in which case it could well be considered fraud. But for the moment, let's not immediately say it's fraud, but somebody's intentionally doing something, but maybe they don't understand what they're doing. And it could be unintentional. And then finally, there are unknown factors that we have no control over. And as an example, just a few years ago, a group reported that had discovered that if you're doing experiments on rodents, for the particular experiment they were doing, that it mattered what the gender of the technician who was doing the experiments was. The rats, or mice, I think it was mice, were calmer when female technicians were injecting them than when the male technicians, so it resulted in different experimental results. Now, notwithstanding the fact I don't know if that study has been reproduced, but I can tell you that it's a reminder that sometimes there is something that might be a factor that you never even anticipated. So if we're looking for solutions to improve the reliability of the work that we rely on, the reliability of the work that in bioethics you might turn to make judgments about what should one be doing, how should one think about this problem. If we want to do that, then we should be thinking a lot about where those failures occur that are unintentional in the areas of design, documentation, and what's reported. And what I have found, and I've taught a lot of workshops on this topic in San Diego and elsewhere, is that it is really incredible how often there are lots of useful things that could be done. They are really easy and inexpensive, and they are almost never done. And that should disturb us all, but instead of being disturbed, it should challenge us to say, we can do better and try and find the way to do better. So how can we do better? We should change the system to reward researchers, provide adequate training and mentoring for the next generation of scientists, and they design their experiments to minimize the risk of bias. They design their experiments with adequate controls. They keep good records. They understand and use statistics appropriately. They report accurately what was done. These things should sound so obvious and so simple, and they are routinely not done. So it would be surprising if a really high percentage of what's published were reproducible. we should not be surprised at the lack of reproducibility. And then finally, align criteria for success with quality of scholarship, not with whether you've published in a high impact factor journal. So I'm going to stop there, leave us a little bit of time for questions. So thank you.
Who has a question?
And you need to tell us which graduate program you're a graduate student in.
I don't come from this century. I have two questions, and they may be related. One is you've stipulated that journals have citations, articles, if you will, and so forth that are relied upon or not. But journals are edited.
Mm-hmm.
And therefore it raises questions about the editing itself. You haven't addressed that.
Yeah.
The second part of the question is that at a time when communication was very, very diminished, and there were the periods of time between a discovery or research and its usability or reproducibility was quite lengthy. The discovery of quantum theory based upon a series of experiments that had been done, each of which was separate and then collected, if you will, not in journals, but simply by word of mouth and then communication between the principals. How do you relate to the potential editorial flaws in judgment and the simplicity with which the discoveries that ultimately lined up and produced the B equal MC squares and so forth in quantum theory? How do you do that and feel comfortable doing it?
Okay, I don't feel comfortable doing almost anything, but I will. So two parts to this. I mean, first, let's just talk about the role of editors. There are multiple stakeholders involved in this process, and they all have something to answer for. Editors, peer reviewers, publishers, funders of science, all of them have roles. The role of the editors, which I think you're alluding to here or stating, is that editors make decisions about how hard they want to push authors for certain things and whether they want certain sexy things in their journal. One of my colleagues at UC San Diego was the editor of the Journal of Clinical Investigation for 5 years, which is a high impact factor journal, as it turns out, but he became upset with what he saw of the editorial process and continues to talk about this a lot, where editors do things to game the system for the sake of impact factor and for getting people to read their journals. And in a certain level, you say that's a reasonable thing to do, but if it means throwing out some work because it's not sexy enough for your journal, but in fact it might be important later, or it means holding papers up for publication so they can be all published at the same time as a bundle so that people will come to read that. The question is that the role of the editor? Should the editor do that? And the fact is that editors do that for at least some journals. So there is a risk, and I think that's what you're saying, that the editors could be driving certain kinds of research to be problematic. The second example, I'm not familiar with the history of quantum theory and the publication record, but if I'm understanding correctly, you're saying that there was kind of an open, almost discussion that was ongoing in the field, and ideas evolved collectively together, as opposed to saying, here's one big paper that's published now, and now we have the answer. Is that a correct view of it? Yeah. So, and I think there's a lot we could discuss about whether the model of publishing we have now is the best way for communicating science. There are some fields, physics is one of them, where there's and bioarchive is an example of the same thing, now where it's possible to basically put out what you're doing for others to start looking at. Others can work on it as well, but everybody's sort of looking at this work together as a community, and then you refine it before you try and publish it. And some, but not all journals would allow you to publish after having published in that kind of a communication forum instead of a formal publication. And I'm thinking that from the physics field, that's almost certainly what things were probably like as the ideas of quantum theory were developed. I don't know if I've understood your question correctly, but yes.
Hello, I'm the new data services librarian here. Just started a couple months ago, but one thing that we've been doing in the libraries for a long time here and other places is trying to help with things like reproducibility through data management plans. And we always hit a roadblock because we have very little interest from researchers to do better data management or to pre-plan some of their research. So I'm wondering if you have any insights on how we can reach faculty, because it's been something that's been really difficult for us.
Yeah, so one of the things that I've been forced to learn about is marketing and in the different kinds of things I was doing to try and succeed. So I'm going to answer one way as a little bit of orthogonally to what you're talking about. We have a librarian at UC San Diego. Her name is Allegra Swift, and she has been talking to researchers about how to quantify the impact of their careers, because many researchers, young researchers, starting to worry about a system that focuses just on impact factor, wondering how do I make the case that I should get this job or I should be promoted. And there are lots of different ways to do that. And I think there's a lot of interest in that because people have interest in figuring out how to succeed and survive. And so she's giving them tools to work around a flawed system. As far as the data management is concerned, I would answer the same way I try and make cases for people to take ethics courses, is it's probably a bad idea to start by saying, I'm going to tell you how to manage your data because you're badly managing your data, and it's a bad idea to tell somebody, I'm going to teach you ethics because you're unethical. And instead to say, we have a space here that we've created in this course or workshops, whatever you might have, where we are going to provide you with some tools that might help you be more successful in your research. And those tools in data management might be things like, where can you back up your data so when your building burns down, you won't lose 3 years of research? Or it might be, that could be not just electronic data, but it could be cell lines. If you do cell research, having those cell lines in a freezer in a different building so that they aren't all lost. Data management has many different aspects, but you can imagine going through each of those and saying, we're just here to talk to you about ways to help you have a more successful career trajectory, make things easier for you. You probably tried that. That's some ideas.
Well, let's all thank Dr. Kalichman for coming up to Santa Barbara.